So this example is a tricky one. It's the drinker's paradox, and what it says that here, there is some guest in the pub such that when they are drunk, then everybody's drunk. So it all depends on a single guest. Now let's see how this is modeled, and let's see if that is really true or if that's satisfiable. So now the first thing is we have to model guests. So now here it's a bit simplified. So we're just modeling some data type guest, and they have different values. So now there's 5 guests, but we could model this differently. We can have more guests here, and then basically in addition to this data type that basically has the elements which are the guests, we also define a function that tells us whether a guest is drunk or not. So this, for every value of guest, this must assign true or false. And then we start expressing our assertion that there exists some guest X. Now, we don't know which one, right? We don't care which one is the special one, but there is a special guest that if the guest is drunk, then everybody's drunk. So if drunk X is true, this implies that for all of the other guests Y, they are also drunk. Now let's check if this really is true. This would be very strange, right? That is satisfiable. Now, what did we actually check? With satisfiability, we checked whether there is some scenario where there's some guest, and if they are drunk, then everybody's drunk. Now, what we really might want to check is we don't want to just check satisfiability of this, but validity. Now, to check validity instead of satisfiability, what we can do is we can negate the thing that we're checking, and if there's no way to satisfy the negation, then it must be valid. So it must be then satisfied for all possible assignments to the variables. So let's negate this. Let's put a not around this thing, and then check again satisfiability. Now it's unsat. So this means really that no matter what values, there's not just one lucky guess of value X, a special one. There's always exists some X that if X is drunk, then everybody's drunk. How can this be? So maybe let's remove this negation again and have a look at the model. Right, we can not only check sat, we can also ask get a model. That's an odd model, right? This model here says, well, let's take all the guests and let's define the function drunk to always return false. So this means nobody's drunk. Actually, what happened here, and that's one solution, and there are many possible solutions. If nobody's drunk, then we always pick a guest X that is not drunk. And then the left side of this implication is false, which means the implication is true. So that's an easy way to satisfy this. We could pick a guest who is not drunk, and then the left side is false, and then it doesn't matter whether all the other guests are drunk. This implication, left side false, is already satisfied. In the other case, in case we cannot find a guest who is not drunk, then of course all guests will be drunk. Otherwise we could find one, right? So basically this is some difference in the way the intuitive natural language description of the sentence says it. If there's one, there's always one guest. If the guest is drunk, then everybody's drunk. That's not really exactly what the logic adaptation maybe suggests, because intuitively we don't really think of this case that this guest X isn't really drunk, and that's how we satisfy this implication. We usually would think that, well, there must be somebody who's really drunk. Okay, that's the drinker's paradox in SMT.